Electrochemistry involves oxidation and reduction parts of wire. So we already know that a redox reaction involves a transfer of electrons. The electrons come from the species being oxidized, and the electrons, those same electrons, go to the species that's being reduced. So oxidation is electron loss, reduction is a gain of electrons when you describe it in terms of the electrons. Well, electrochemistry, just because you have a redox reaction doesn't mean you have electrochemistry. Electrochemistry is when you take that process, that reaction, and you physically set up the reaction so that the only way the electrons can move from what's being oxidized to what's being reduced is through a wire. So you force the electrons to have to go through a wire in order to go to the species to finish the reaction, to finish the redox reaction. And the only way to do that is to really physically separate the oxidation part of the reaction from the reduction part. Usually that's done by completely separating solutions that would normally be mixed together into separate containers and connecting those containers with a wire. And those separate containers you would call half cells. The entire setup of the redox reaction that takes place this way, the entire setup is called a cell. When you have a cell in electrochemistry, it's a combination of both the oxidation and reduction together, but being connected by a wire. So if I take this reaction, this redox reaction, zinc solid plus copper, let's say this is copper sulfate. That can produce zinc sulfate and solid copper. So the copper here would be a solid, the zinc here would be a solid. These two would be in solution, they'd be aqueous. So that's a whole redox reaction in which electrons are transferred from the zinc. The zinc loses the electrons. The copper gains those electrons because copper here starts out as a 2+. So this is showing the whole reaction in what in Chem 1 we'd refer to that as a molecular equation. I'm going to write this same reaction in a net ionic form, and really this is one of the reasons why you guys have learned about net ionic equations, is so that you can analyze electrochemistry from that point of view, because it's a lot simpler when you don't include the spectator ions. So I'm going to rewrite this, the net ionic equation. So what we want to do is first think about this as two half reactions. So you have the zinc being oxidized, and you have the copper being reduced. Those are the half reactions. The first half reaction represents the oxidation. What would be called an oxidation half reaction. Okay, so far I've analyzed it with half reactions, but I haven't shown yet how it's actually electrochemistry, because I haven't shown what the electrochemical cell and half cells could look like in a situation like this. So I'm going to keep in mind these two half reactions, but I'm going to erase this board and show you the cell and the half cells. To do that, I have to draw a picture of what the physical situation could be. We're going to have a beaker that contains the, say, the copper solution. Okay, so that would have copper 2+. That would be copper sulfate in this case. So you'd have copper 2+. You'd also have sulfate ions in there. Okay, but we're going to assume the sulfate doesn't do anything. It doesn't react. And then another beaker close by. And the other beaker has a solution that's made up of zinc sulfate, because zinc is going to be produced. It's not there, it's not a reactant, but it is a product. But we're going to go ahead and have it here in this solution, zinc 2+, and then that's also going to have sulfate in it. Okay. So we have copper 2+ and zinc 2+. Those are two parts of our reaction. But what else is in the reaction besides copper 2+ and zinc 2+? Now, copper 2+ is a reactant. So I could over here show solid zinc, but I don't want to do that, because if I showed a piece, I'm going to have it sticking up out of the solution, and you'll see why in a minute. But if I have a piece of metal here and I make it zinc, that's not electrochemistry, because the zinc would react directly with the copper and the electrons would just be going back and forth right here. There would be no external wire. So I'm not going to make that metal be a piece of zinc. I'm going to make that metal be a piece of copper. Solid. Okay. Make that copper. And then I'm going to put another piece of metal here, and that's going to be where I'm going to put the zinc. So it's a piece of solid zinc over here, piece of solid copper here. The reaction has this reacting with this, but they're not connected to each other, so they can't react in the way I'm showing in the picture. However, if I connect this piece of zinc with a wire to that piece of copper, so this is a wire, what I'm doing is I'm allowing the electrons from this piece of zinc that want to join with the copper, I'm allowing them a path to do it, because they're actually being attracted by that copper. That's what a potential is. It's an attraction or a repulsion. It's a pull or a push. It's a force, really, on the electrons. And that zinc piece feels that force. The electrons on the zinc feel that they want to go over here, and now I've given them a path, so they're just going to go through the wire. They're also going to go through the copper metal, because it's a conductor, and they're going to come out here and join with the copper on the other side. So when the electrons that come from the zinc are going to travel through the wire, okay, so these are my electrons, going to travel through the wire, then they're going to jump from the piece of metal to the copper. So this is, again, an electron that's now in the solution. That's really bad focus. Can you see that any better than I can? Can you make out that this is an E?
No, I can't make the E
I
out.
didn't think so. So anyway, that the blue represents electrons. We'll just say that. I think you can kind of tell that it's blue. But that's what's happening here. Is the electron comes in here, goes to the copper, and then it jumps over to the copper metal. And what it does is it jumps over to the copper ion, and it turns that copper ion into copper metal. So the copper metal then ends up attaching to that other piece of copper that's already there, and it deposits on it. it forms a deposit of copper on top of the copper that was there already. As a matter of fact, you don't really even need this to be copper in order for this reaction to work, because all you have to have here is a conductor. Okay, this could be a piece of graphite where the electrons can go in here. Now there is still copper solid that's going to form, but it could form on top of anything that you put in here that can carry a charge. You don't want this piece of metal to be something that could react with the copper though, so that's why you would either use the same metal or maybe use graphite. Graphite is just carbon and it's not going to react directly with the copper. So that together, this whole picture is an electrochemical cell. Okay. And in the electrochemical cell, you have half cells. So this one involves the copper picking up electrons. So this would be the reduction. And this would be the oxidation. And both of these then would be half cells. A cell like this, though, that occurs spontaneously is called a galvanic cell. Also, sometimes you'll use the word voltaic. That's the same as galvanic. You can either refer to this as a galvanic cell or a voltaic cell, but it means a spontaneous reaction is taking place here. One other thing, for this reaction to occur for any length of time, you have to be able to restore the charge in the two solutions, because right now physically separating them kind of creates an artificial environment where you're draining charge out of here because it's going, out of here because the electrons are neutralizing the copper. So you're kind of building up basically what would be a negative overall charge because you still have sulfate in there. To balance that, you have to connect the two cells with something physical that will allow ions to pass from one side to the other. If you had a different setup, you could make it some kind of a membrane where ions can pass through it. But most of the time, the ions are supplied by what's called a salt bridge. So you can place in here something that connects the two with some kind of a solid or a you could even take a paper towel and soak it in an ionic solution and drape it over between the two beakers, and that would do it. Just something that has ions in it that could drain ions where they're needed to keep the solution neutral. So this piece right here, the salt. One other thing I wanted to mention here, and this just has to do with terminology. The half cell where reduction takes place is called the cathode, and the half cell where oxidation takes place is called the anode. So right here, this reduction side would be the cathode. Now usually, sometimes you just refer to the connection itself as being the cathode, because that's also, involved in the reduction, but you could also refer to the whole thing as being a cathode. And then the other side where oxidation takes place, over here you'd have the anode. So you could say the zinc strip is the anode of the cell and the copper strip is the cathode of the cell.